The third law of thermodynamics says that the entropy of any element in the perfect crystalline at 0 Kelvin has an entropy of 0. So if you're moving from reactants with entropy SR to products with entropy SP, the change from reactant to products according to the definition of a state function does not depend on the path. The change in entropy is going to simply equal the entropy of the products minus the entropy of the reactants. We can define the standard entropy change for any reaction to be the entropy change for the reaction carried out at 1 atmosphere and 25 degrees. In this case, the change in entropy for this reaction is going to be simply the sum of the entropy of the products multiplied times their number of moles minus the sum of the entropy of the reactants multiplied times their number of moles. It's the same mathematics that we learned for delta H in chapter 9 is going to be the same when we discuss delta G later on. It's basically the sum of the products minus the sum of the reactants. One important difference here is in case of delta H of the reaction, it was the difference between the change in enthalpy of formation for the products minus enthalpy of formation of the reactants. So this is the change in enthalpy of formation for the substance, while here in case of entropy, it's actually the absolute value for entropy for the substance. It's not delta S for the substance. And it's a very common point of confusion between the two types of math. What is delta S for this reaction? Delta S for any reaction is going to equal the sum of number of moles times the entropy of the products minus the sum of number of moles times the entropy of the reactants. So it's going to equal 1 times the entropy of calcium oxide, 39.8 joule Kelvin mole, plus 1 mole times the entropy of carbon dioxide, which is 213.6 joule Kelvin mole, minus the reactants, which is 1 times the entropy of calcium carbonate, which is 92.9 joule per Kelvin mole, which gives us plus 260 joules per Kelvin mole. And we could have predicted that it's going to be a positive change in entropy because we're moving from the ordered solid state reactant to less ordered or more random gaseous state products. So that's a positive change in entropy for sure. For this reaction of nitrogen with hydrogen to make ammonia, what would be the change in entropy? Again, we could make a prediction about the sign by comparing the number of moles of the reactants, which are 4, to the number of moles of the products, which is 2. So the change in number of moles of the gases involved in the reaction is actually diminishing. And as we said, when the number of moles of the gas is diminishing, this is going to be a negative change in entropy. But we can calculate the actual value using products minus reactants math. So delta S for the reaction is going to be number of moles times S for the products, the sum of the entropies of the products, minus the sum of number of moles times the entropies for the reactants. So it's going to equal 2 times 193 joule Kelvin mole. These are the products minus the sum of the reactants, which is going to be 3 times 131 joule Kelvin mole plus 192 joule Kelvin mole, and that is going to give us negative 199 joule Kelvin mole, which is the same sign as we predicted in the beginning. Let's go back to this example right here. Question here is asking us to calculate the value of delta S6, and as we know, the change in entropy for any process is going to equal the entropy of the final state of the system minus the entropy of the initial state of the system. The final state of the system is a solid at 0 Kelvin, which according to third law of thermodynamics is going to have an entropy of 0. So the final entropy of the system is 0. The initial entropy of the system is a gaseous phase at 25 degrees, which is the standard molar entropy of the sample as given by. So the initial state of the system is actually 223 joule Kelvin mole. So delta S6 is going to equal 0 minus 223 joule per Kelvin mole. It's going to equal negative that number.